Right. Power grid maintenance. This is from weekly contest. You're given an integer C. This represents C power stations, and each unique identifier. Basically, every power station has a unique identifier. Starting from one index, they are interconnected with y-directional cables, represented by connections array, 2D array. UI VI basically represents a connection between them. Stations that are directly or indirectly connected from a form of power grid. Initially, all stations are online. Uh, we have two 2D array queries in which 1 comma x and 2 comma x is the format. 1 comma x means a maintenance. Basically, in a maintenance, if a station is online, then it is well and good. If it is offline, then the check is resolved by the operational station with the smallest ID, right? That is X, whatever in that uh, power grid, the online station that we have, the smallest among those is what we need to return. If we don't have any other station online, in that case we return -1. 2 comma x represents that x needs to, or x will be going offline in this query, and we need to return answers for the 1 comma x query in the order they appear. Structure is preserved. That means if our or a station goes offline, then the adjacent stations are still connected. It doesn't mean that they are disconnected now that it went offline, right? So here this question screams uh, DSU, right? And that's how we are going to solve this problem. Basically, in order to uh, achieve this part where we need to return the smallest uh, station that is present in the power grid, which is online, we can have a set, right? Ordered set will be maintained, and the as any of the station goes offline, then we remove it from the set, right? And yeah, once it is removed, it is not said that we add that back, right? So there's that, and I guess that's pretty much it, right? So if we divide it into steps, then we need DSU. We will iterate through the connections array and generate the DSU, right? Uh, Iterate connections array and populate DSU. This data structure alone is not helpful, so we need a ordered set along with it, and this ordered set will initially contain a tree set. Sorry, not a tree set. Tree set is in Java. Ordered set, but this ordered set will essentially be the one that is uh, represented by the parent node of a power grid, right? Since we are going to use the find parent function for a node to get its parent, that parent node is going to be the one which is going to have a set, right? So in that case, we can have multiple components and hence multiple sets. That's why map makes sense here, right? This makes sense here. Why? Because this key is going to be the parent, and for every parent that is going to represent a component is going to have a set, right? So when we merge The merge function is going to have the logic of unioning the two sets into one and updating the one which is going to have a higher rank. That's going to be the parent, right? So yeah, merge function contains logic for unioning the two sets into parent key in map based on rank. Sorry for the bad English. Alright, so let's code this up. Uh, I need to have a class union, which is going to have, let's say, public uh, vector of parent, vector of rank, right? Unordered map is going to be a key to a set, right? Mapping. Let's say this is called online. I am going to have a union constructor in which parent is resized to resized by the number of nodes, and the same goes for the rank. The parent is not just initialized, not just resized, but initialized to the node itself. Basically, it is a self-pointing node at this point, right? So here I just need to initialize the parent node. Every parent or every node is a self-pointing node, and at this point I can also, basically it is said that initially all stations are operational. That means they are individual components. Each node is forming a power grid, and I can just have n number of sets at this point, which is a little redundant, but that's because we have a merge function which is going to have the logic of merging the two different components when we are connecting them by the edges, and that's the reason we need to have separate sets, because we are going to union them when we do the merge. Okay, so at this point this is the case, this is the node and this is the set, and I can have a find parent function in which a node is passed with path compression. We can optimize this. N is equal to parent of n, right? And I can return n at this point. Basically, this is what path compression is, right? We are just not just jumping here, but we are jumping this in this manner from this particular node. If this is the parent node, then the jump will be ultimately like this, right? Twice I'm going to point to the node itself, reason being the parent is always going to be the self-pointing node, right? That's how we are structuring the parent node or parent array. So this is the find parent function. Bool merge is going to take two nodes, right? And P1 is going to be the parent one. Using the function, I can find it easily in approximately constant time, right? Uh, P1 is equal to P2, return true. If they are already part of the same component, we return true. Otherwise, we basically check the rank right? And we basically see if rank of P1 is more, then parent of P2 is equal to P1, and the rank of P2 or P1 is increased, and lastly the set of P2 and the set of P1 is both combined and updated for P1 because P1 is a parent, right? So essentially online of P1 is the parent, and I'm inserting everything that is contained in the set of P2, right? So essentially online of P2 dot begin and online of P2 dot end, right? And the same thing but quite opposite is going to be the else condition. P1 is equal to, sorry, parent of P1 is equal to P2. In this case, rank of P2, online of P2, and this will be P1, and we can return false in this case. I believe that returning anything doesn't even matter because we are not going to use the return value. So essentially, a void function is also good, right? Nothing I need to return from here, right? So we're good with the function. I also want to have a function for handling this query, that is the turn offline query. So here turn offline uh, uh, it takes a node which needs to be turned off, and I am going to use the find parent function to find the parent of this node, and essentially from the set of P this particular node needs to be removed, right? So basically I'm sorry, P dot erase n is going to be the function. Lastly, this query also needs a function 1 comma x, which is essentially a perform maintenance. So let me rename that perform maintenance. I guess this is the, let me copy this. Alright, and this is also taking a node, finding the parent, I'm sorry, alright. If at this point I'm going to check the set of P if it contains or if it is empty. If it is empty, I can return -1, right? Otherwise, I can check if the count of n, right? And based on that, I can return if it is present in the set. In that case, I can return n because it is going to resolve by itself if it is already online. Otherwise, I can return the first element in the ordered set, which is going to be extracted using the begin function, and this is going to return the iterator, and I'm going to get the value using the pointer or the address. At this point, I think we're good with the union class. So here a union root is going to be prepared. Mind that this is one index based, So it's going to be C plus 1, not just C. And I'm going to iterate the connections array, and basically for every edge a merge function will be called. Connections of I of 0 and I of 1 is going to be merged. Let's arrange our answer array and iterate the queries array, where for every query I'm going to get the node, because regardless of the format, every array or every query is going to have a second element as the node. At this point I'm going to check if it's a 1. If it's a 1, in that case I can push this one, because it's a perform maintenance 1 which we need to push in the answer. So let's push this guy. Whatever this guy will return, I'll pass the node here. Else I'm going to call the turn offline function which we have prepared, and this is also going to take a node, right? We can return the answer. Let's see if this works. Okay, a semicolon. Okay, something is not right. Let's see. Queries of I of 0, if it's equal to 1. I'm sorry, it needs to be equal to 1, right? Because 2 is also going to, uh, you know, it's not right condition. So now this works. Let's submit this. Time complexity wise, let's see. Uh, I should uh, technically check if P1 is already equal to P2. In that case, of course, this is redundant. It doesn't do anything instead of just using up time, right? I can just return here itself. Otherwise, I need to merge if they are not part of the same component, right? Time complexity is going to be, merge function is going to be O of 1, or approximately O of 1. So this is going to be O of n operation, and actually it's not going to be O of n operation, because we have modified it using a set which is going to take a log operation, right? In that case, a set might have half of the elements in one set, right? So this is going to take a kind of log n by 2 time complexity, making this log n, which is going to make this O of n log n. Again, it's approximation. Here it's going to be O of q, and for every query we are doing a perform maintenance and turn offline, which is again a log operation, where this is again erasing things, so it's a login, and this is uh, yeah, this is kind of O of 1, right? So in worst case is going to be O of Q into log N, right? Yeah. So that's the time complexity. Space complexity is again O of N, makes sense here, right? And yeah, let's keep this question here. Let's move to the next question. Here, minimum time for key connected components. We are given n and an undirected graph with n nodes 0 to n minus 1, edges array in the format ui, vi, and time, indicating edge between ui and vi such that it can be removed at time this. Okay, and integer k is given, and we are told that we need to find the minimum time t such that after removing all edges with time t with time less than equal to t, at least k connected components are left, right? So essentially, this is kind of uh, hints towards binary search, because if we do a logarithmic uh, operation of search of time, and for every decided time we are doing a O of n kind of operation, making it a O of n log uh, I guess k, or not k, probably the search space is going to be the, yeah, I'm sorry. So basically we are given edges in the format ui, va, and time, right? And we are essentially choosing a time which is going to be such that all the edges below that decided time is going to be removed. So essentially, we can sort this array and do a binary search of a time and basically iterate from the back. So, so essentially, sort the array of edges based on time. This will help us allowing to perform a binary search, perform binary search on a time search space of what? Basically, since we have sorted the array, we can get the search space easily. This search space will be starting from 0 and moving till end, which is basically the last edge that we have sorted, because that's the most right. If it is x, then the end is going to be x, reason being all the edges can be removed at time x, right? So essentially, edges of or back 0, 1, 2, right? So this is what we can do, and we are going to use the union function from the previous problem, which is going to be very similar, right? And the most important part is using the valid function, or how the valid function is going to work, because we have decided on a particular time, and we need to see if that time leads to a k connected component at the end or not, right? So if it is leading to the k comment connected component, in that case we move to the left, reason being we need to minimize the time, Otherwise, we move to the right? So let's code this up. Let's copy the union function or union class. We will remove the set part from this. So we don't need the set. Let's keep the rank, right? I think I can just do a iota, right? And this is starting from 0. And this time we need to know the components, right? So starting from uh, right from the start, let's keep the component as the number of nodes, right? So let's initialize components to be n, and as we merge, we are going to uh, remove the component count, and that's going to be done here. Since we are merging at this point, we can reduce the component count. We don't need this, we don't need this, and we are good, right? So we are going to sort the edges array. So let's sort it based on the third element. Return uh, LHS of 2 less than RHS of 2. Get the length, uh, get the search space. So at this point, if since we see in the constraint that edges can be 0 as well, if it is 0, that means there are no edges, right? In that case, the end will also be a 0 instead, right? So we have to be careful here. It needs to be a 0, otherwise I can consider the last edge value, right? And my answer from the get-go is going to be the end, and I'm going to minimize it. So while start is less than equal to end, I'm going to get the middle, start plus end by 2. If it is valid, so let's create a valid function. In that case, what all things do we need to pass? We need to pass uh, the value that we have decided upon, that is mid. We need to pass the edges array. We need to pass key, right? And we also need to pass node, since we are going to create the union function inside this is valid function. So we need we need nodes count for that, and n is what uh, is represented by the node count. So answer is equal to mid at this point, and since we have found it valid, then we move to the left, making end is equal to mid minus 1, else start is equal to mid plus 1. So at this point we can return the answer, and let's create the is valid function in which we take k, we take time, we take edges, because we are going to iterate and basically form components. So a union, let's call it root, is going to be created. And let's start from the back. Reason being, since we have sorted it based on time, we are going to continue having or keeping the edges which are greater than t, which ultimately means that we are not merging all these edges which have a time less than equal to t, in our case less than equal to time, right? In that case we are not going to merge it, which ultimately means that we are not keeping those edges, right? Because we have removed it. So let's keep the last element or last position as the index while I is greater than equal to 0. If edges, if we are at a point that the second position value is less than equal to the decided time, in that case we can just break, right? Otherwise let's merge edges of I 0 and 1, right? And do I minus minus. Return the check that is going to be if the number of components at this point, which is essentially this, right? Root dot components is equal to k. If that is the case, then we are good. We return true. Otherwise, we return false. Right? Let's see if this works. It does. Let's submit this. It needs to be at least k connected components and not exactly k connected components, and that's the mistake. The time complexity will be again the sorting is going to take O of uh, n log n if n is the number of edges. Then we are doing a search space where the maximum value of time can be 10 to the power 9. So that's going to be a logarithmic max time value, right? And for every value we are going to is valid, which is again in worst case going to be the number of edges, right? So n into log max time is going to be time complexity for this particular loop, and probably the dominant one as well, right?